Hello, everyone. I'm Dr. Tania Sharmin. I'm an assistant professor in sustainable environmental design in architecture at the Welsh School of Architecture at Cardiff University. And in this presentation, I'll be talking about traditional comfort practices of a low-income community in Ahmedabad in India. So the community is called Loving Community, named by the Gandhi Leprosy Seva Sangh. It was formed in 1968 after the land was provided by the government of Gujarat to accommodate leprosy-affected people from all over India who were socially excluded due to the contagious nature of the disease. The community has 125 houses with a population of approximately 500 people. We know that Indian people have a diversified culture and adaptive behavior, which needs to be acknowledged in the thermal comfort studies. For instance, in the hot dry climate zone in India, it's a common cultural practice to sleep in outdoor courtyards, roofs, or semi-outdoor spaces like balconies during the summer months. Outdoor sleeping is further coupled with night ventilation and diverse seasonal and diurnal occupancy pattern as a part of the living style. This does not mean that the indoor spaces are less important in terms of thermal comfort for other household activities. To provide comfortable habitat for these people, it's therefore important to gain understanding of their living style and cultural practices to ensure appropriate application of indigenous strategies to combat adversities of the local climate. So here are some photos from the common areas within the community, you can see. So in this study, basically the community has three different types of houses. So here is the type 1 houses, which are new builds. And these are generally 2 or 3 story buildings constructed by individual owners with local contractors without any architect's supervision or involvement. And these are built up with minimal cross ventilation and daylighting options. The rear room generally does not have an outside window or daylight access. And building envelope, as you can see from the images, consists of a brick wall with plastered finish with concrete roof slab. Type 2 houses, DMU new builds, built under a charity program by the De Montfort University in the UK. These are typically one-storied buildings designed and built by C-Lab architects. Building envelope consists of brick wall with a plastered white finish with concrete roof slab. Some of these houses are 2-storied and have a ferro cement roof mesh with white tiled surface on the top. Natural ventilation and daylighting have been maximized in all these buildings with the stacked ventilation in the 2-story buildings. And the courtyard has been incorporated for social as well as environmental reasons to provide mutual shading and cross ventilation. Type 3 houses or the old houses, these are the original houses in this community, 1-story buildings originally constructed under the government initiatives. In this case, the rear rooms do not have any natural ventilation or daylighting. The wall consists of single file brick walls with plaster finish with a corrugated iron sheet or tin sheet roof, as you can see in the image. So I conducted an indoor thermal comfort study within 12 households of these 3 different house types. A standard thermal comfort survey was carried out alongside immediate measurements of air temperature, relative humidity, wind speed, and mean radiant temperature using the Testo 480 data logger, as you can see in the picture. The thermal sensation was recorded using ASHRAE comfort scale, and simultaneous air temperature and relative humidity measurements over a 3-day period was also carried out using HOBO data loggers to investigate the thermal performance of different house types. So a better look at the environmental aspects of these three types of houses. So in the type 1, these are nicely built with robust material, as I've just said before. However, there is a serious lack of natural ventilation and daylighting. And you can see some of the living rooms which does not have any windows or cross ventilation. The thick walls are actually helpful to reduce conductive heat gain during daytime in summer, but without cross ventilation, it means nighttime temperatures are above the comfort limits. In the type 2 houses, the architect has incorporated front courtyard in all type 2 houses and a back courtyard in some of them. The front courtyard provides mutual shading and space for day-to-day social interaction with the neighbors. Additionally, the architect has incorporated roof extractor fans to increase a stacked ventilation effect alongside cross ventilation through the windows. He further used a foldable window door, as you can see in this image, the blue doors, to maximize cross ventilation when necessary. These ventilation strategies are effective to maximize night ventilation and thereby can improve comfort levels due to the large diurnal temperature swing prevalent in this region. In this image, you can see the back courtyards, which basically serves as a space for cleaning the utensils and washing and drying clothes, alongside ensuring privacy for women. The other critical role of the back courtyard is to facilitate cross ventilation, especially because the houses were originally arranged back to back by sharing a common brick wall. So the only way cross ventilation could be arranged was to make provision for a back courtyard. In the type 3 houses, which are the old houses, you can see these are tin shed. These have tin shed roofs, which become extremely hot during the daytime, and the inner room has no window, no provision for cross ventilation. So I'll present some of the results. This particular graph shows that the old houses have the greatest fluctuation and highest temperature with an average temperature of 36.8 degrees Celsius. The acceptable thermal comfort limits for naturally ventilated buildings in this region is within an upper limit of 32 degrees Celsius and 60% relative humidity, provided an air velocity of 1.6 mile per second. The maximum temperature of 47.6 degrees Celsius was recorded at Old House 1 on the second day. And the lowest temperature was 32.6 degrees Celsius recorded at a DMA new build, the type 2 houses, on the first day. So basically these images shows the average temperature conditions in each type of houses, but the maximum temperature was like 47.6 degrees Celsius. And the maximum difference on air temperature was found to be 12.8 degrees Celsius recorded between Old House 1 and DMU New Build 3 at 12:50 p.m. on the second day. So the air temperature in the new build houses is more stable with an average temperature of 36.8 degrees Celsius equal to the old houses. DMU new build, on the other hand, had the lowest average temperature of 35.8 degrees Celsius during the above time period. It means even in a very hot condition, passive strategies applied in architecturally designed buildings, as in the type 2 houses, were able to reduce air temperature compared to the new buildings when you compare to the other new builds, which are the type 1 buildings. So all respondents, this is the thermal comfort chart showing the thermal sensation vote across the 3 different types of houses. So all respondents in the DMU new build houses felt comfortable or neutral during the survey period, whereas the thermal sensation vote or TSV for people in the new build and the old houses varied between neutral to warm and warm to hot. In the old houses, 100% people felt either warm or hot. This corresponds with the air temperature measured in the houses. In the type 1 houses, the responses were comfortable, slightly warm, and hot. There was no response in the cold, cool, or slightly cool category for the extremely hot conditions. So it's quite remarkable to see that people were comfortable in the type 1 and type 2 houses at an average air temperature of 37 degrees Celsius. It could be basically due to their overall satisfaction with the housing condition, as well as their ability to acclimatize with the high air temperature conditions linked to their daily livelihood. So basically, many of these people are beggars, and also their livelihood is linked to outdoor type activities. So they mostly work outdoors. So maybe that is the reason that their thermal acceptability level or thermal sensitivity level is really quite high. So when asked about the overall living quality of the houses, 100% people in the type 1 and type 2 houses expressed satisfaction. Respondents in the type 3 old houses, on the other hand, were fully dissatisfied. Undoubtedly, environmental conditions with an average air temperature of 40.6 degrees Celsius were unacceptable to most of them. Furthermore, the residents are mostly involved in outdoor type professions, as I just said. It includes auto or manual rickshaw driving, road cleaning, begging, or factory work, which indicates that their acclimatization to a high air temperature ranges. This figure shows how the probability of thermal acceptability decreases with the increase of instantaneous indoor air temperature. So basically, the finding of this study includes that people in the architecturally designed houses, which are the type 2 houses, were fully comfortable even when the temperature ranges were above the prescribed comfort ranges. The average indoor air temperature in the type 1 and type 3 houses was 1 degree Celsius higher than the type 2 houses. Consequently, all inhabitants, 100% of them, in the type 3 houses were found uncomfortable, and only 33.3% people in the type 1 houses were found comfortable during the survey period. This implies that passive design strategies as implemented through architectural design has an important role to play for ensuring thermal comfort in low-income housing. The residents, however, have little knowledge about the adverse effects of poor indoor thermal comfort. Therefore, they could neither fully appreciate nor exercise the full potential of the applied passive strategies. For example, use of courtyards in the design was considered to be a waste of space, considering the acute space shortage and high number of occupants. Similarly, full natural ventilation potential could not be achieved during nights due to impractical window design and lack of safety features in them. It indicates that future design needs further exploration of practical aspects, usability of spaces, and privacy requirements of the occupants in residential spaces to ensure passive design strategies are more effective in practice. So thank you very much, everyone, for listening. Goodbye.